Hi, good morning, everyone. Good morning.
Hi, sir.
Good morning. On a scale of 0 to 10, how much do you hate me?
So don't hate you, sir. It's kind of hard. But it's okay, sir.
But I told you, I'm giving you more challenges. I want to train you.
Yes, sir.
Okay?
Yes, sir. Okay.
Right. Fine. Guys, there are a few questions remaining from the previous topic. We'll finish that and start the new one. I believe that you have got the new tube today. People online, please check it. Check your mail. Right. The questions that are remaining from nuclear decay, starting from question 32, page 49. Question 32, page 49. Potassium chloride may be used to flavor food. Potassium chloride contains trace amounts of radioactive isotope of potassium. This decays into an isotope of calcium by beta decay. Complete the nuclear equation for this decay. So the beta particle is -1, 0. So this has to be 40. 20 minus 1, this has to be 90. Okay. Calculate the energy in mega electron volts released when a nucleus of potassium 40 decays into a nucleus of calcium. Potassium decays into calcium. Right. So guys, the calcium and the beta particle, their mass is this given. Potassium nucleus mass is here. So the M1 mass before the decay is 39.963998. M2, the mass after decay, 39.962591 plus 0.00054858. That is going to be 39.963139. I'll take it to 6 decimal places. M1 is also 6 decimal places. Okay, so the delta M, the mass deficit is going to be the difference. M1 minus M2. It's going to be 39.963998 minus 39.963139. That is 8.59 into 10 to the power minus 4 U. This is a mass deficit. Okay, so the energy release will be given by E equals mc square. So the M is 8.59 into 10 to the power minus 4 into, convert this into kilograms, 1.66 into 10 to the power minus 27. Am I right? That is in kilograms. C square is going to be 3 into 10 to the power 8. That needs to be square. This gives you the energy released, but in joules. We want to convert it into mega electron volts. So divide by charge of an electron 1.6 into 10 to the power minus 19 to convert it into electron volts, and divide by 10 to the power 6 to convert it into mega electron volts. Is it 0.802? Have you got this answer? Easy 5 marks. The same thing we have done so many times, and you're getting 5 marks for that. Okay. Explain why there is a range of energies for the beta particles emitted in the decay of a sample of potassium 40. We answered this question also in the earlier one. Why there is a range of kinetic energies for the beta particles emitted. Yes, right. What's your answer? Huh? Momentum is conserved. The energy is shared between the calcium and the beta particle. So the calcium will have a range of energies. Okay, it's a spontaneous decay. So the calcium particle emitted can have a different energies. So the beta particle can have different energy values for the kinetic energy. Okay, right? Momentum is conserved. Momentum is conserved, and the energy is shared by both calcium and beta particle. And beta particles. Full stop. The calcium nuclei can have different energy values or speed. So does the beta particle. Right? We have answered the rest of the question. Part B we have done. And then 33.
So 31.
31 did I ask you to do? I haven't asked you to do, but we'll do it. For homework, I haven't asked you to do. 33. Thorium is an unstable isotope that decays into radium as shown in the nuclear equation. The table below gives the masses of the nuclei. Show that the energy released in the decay is about 5.5 mega electron volts. The same thing what we did in the previous question, we have to do again. It's okay, we'll do. So after the decay, the mass produced is this radium and I don't know whether it is radium. Radium and the alpha particle. So the M2 is going to be 224.02 4.021 plus 4.00260. That is going to be 224.02021 plus 4.00260. That is 228.02281 U. So the delta M will be M1 minus M2, which is 228.02873 minus 228.02281. 228.02873 minus 228.02281. That is 5.92 into 10 to the power minus 3U. So the energy released is given by E equals mc square. M is 5.92 into 10 to the power minus 3, convert it into kilograms, 1.66 into 10 to the power minus 27 into 3 into 10 to the power 8 square. This gives you the energy produced in joules, divide by 1.6 10 to the power minus 19 and divide by 10 to the power 6. That gives you the energy produced in mega electron volts. Correct? Exactly the same thing what you did in the previous one. $5.5278. Mega electron volt. Is that okay? Have you got this answer? Or 5.528 or 5.53? Right. The next one. A textbook states that the kinetic energy gained by the alpha particle when a nucleus of thorium-228 decays is equal to 5.4 mega electron volts. Comment on this statement. Your answer should include a calculation. Right. So guys, we did a similar question last class to what I remember. Now, when this thorium decays, okay, when this thorium, now this is a stationary thorium nucleus. So now when it decays, it emits an alpha particle this way. So when it emits an alpha particle, the rest of the particle will recoil for the momentum to be conserved. Am I right? Like how you stand, I mean, if you are in a boat, let's say the boat is still, okay, on water, the boat is still. You have a, let's say, an iron ball in your hand, maybe about 5 kilograms. Okay, you throw it in one direction. You and the boat will move in the other direction. Am I right? Same thing on the snow, ice surface, when there is no friction or very less friction. When you are standing and when you push someone, you will be moving in the opposite direction. Correct? The same thing when you fire a gun. When the bullet goes in a particular direction, the gun will recoil. For what? For the momentum to be conserved, according to the principle of conservation of linear momentum. So here, the thorium nucleus is at rest. So it emits a particle. So the rest of the thorium nucleus has to recoil, which is what we call the radium. Am I right? Agreed? Fine. So the thorium has a mass of 228. I will take it as 228 U. Radium has a mass of 224 U. Alpha particle has a mass of 4 U. To be precise, it's 200 and thorium is 228.02873. 228.0273 U is the mass of the thorium. Sorry, 02873. Radium is 224.02021. And the alpha particle is 4.00260. These are their masses. Okay. Now, let's say the alpha particle moves in this direction with a speed of v alpha, and this recoils with a speed of vr. Okay. According to the principle of conservation of linear momentum, if I use it this way, 4.00260 u into v alpha is equal to 224.02021 u into VR. Am I right? Momentum is conserved. So on either sides, the u's will cancel off. So I can get alpha particles energy is what we had to find. So I'll get the VR subjected here. VR is going to be 4.00260 V alpha divided by 224.02021. This is the VR in terms of V alpha. Okay, which is 4.00260 divided by 224.02021. 0.017. 867 V alpha. This is a VR in terms of V alpha. Now look at this. What we found in the previous part, the energy released 5.5278. That is the total energy released. Okay. Which is the kinetic energy of the alpha particle plus the radium nucleus. Okay. The kinetic energy of the alpha particle is half into its mass is 4.00260. Okay. Into its speed is, we don't write V alpha square, plus half into the radium particle is 224.02021 U. That into VR square. The addition of these two is what equal to 5.5278. Am I right? So now, since we have VR in terms of V alpha, I can substitute that VR in terms of V alpha and find the V alpha. So we will get an equation in terms of V alpha square, and we can find the V alpha square, and then we can find the kinetic energy of the alpha particle, which is going to be this one. You get the answer. Understood? That is one way of doing it. Exactly. You find the V alpha, and then you know the mass of the particle, and then you can use half mv square for the alpha particle. You get the kinetic energy of the alpha particle. You calculate and see it has to be something very close to 5.4 or no. Anyway, we have to make a comment on this statement. If it is a different value, we can say no, it is not. The question says the textbook states that the kinetic energy gained by the alpha particle is 5.4 mega electron volts. Comment on this statement. Your answer should include a calculation. So you calculate the kinetic energy of the alpha particle and then make a comparison whether it is 5.4 or not. Okay. That is one way of doing it. Another way that I can do is, do you want to try this? Have you done this? Did you get the answer? Give it a try. I'll give you a couple of minutes. So half into 4.00260 will be 2.0013 U V alpha square. Half into 224.02021 will be 112.0101 U into VR square. VR square, I will write it again. 0.017 867 V alpha, that square. So that is going to be 2.0013 U V alpha square plus 0.0357 6 U V alpha square, that is equal to 5.5278. So the addition of them will be 0013 plus 0.03576, that is 2.03706 UV alpha square, that is 5.5278. From here, if you get the UV alpha square, that gives you 5.5278 2.78 divided by 2.03706, which is 2.7136. These are U into V alpha square I'm giving. So what is the kinetic energy of the alpha particle? Half into its mass is 4.00260 U into V alpha square, which is half into 4.00260. This U into V alpha square is what we have found, 2.7136. What is the answer? Five point 5.43 is what I'm getting. This is the energy of the alpha particle. So comment on the statement. Yes, 5.43 we are getting. The statement says kinetic energy gained by the alpha particle is equal to 5.4. So we can say yes to two significant figures. It's correct. Am I right? Those who did it, did you get this answer? No. What was it? 5.63? Definitely no. How is that even possible? The reason the total energy released itself equal 5.5278, which is shared between the radium and the alpha particle. So definitely the energy of the alpha particle has to be less than that. Okay. So 5.43 is what I'm getting. What about the others? You did follow this method. No, different method. I'll give you another method. Now this is what I did is I found there, use the conservation of momentum, and then I found the relationship between VR and V alpha, and I added their kinetic energies together and made it equal to the previous value that we got, and somehow did a hard way and found the value. Okay. Another thing that I can do is another method we can do is now now the alpha particle is emitted this way. The radium nucleus is required. So the mass of the alpha particle is m alpha. Mass of the radium is, I'll take it as mr. Mass of the speed of the alpha particle is, I'll take it as v alpha. Speed of the radium, I will take it as vr. Listen to me carefully. So guys, momentum is conserved. Momentum of this particle, P alpha is m alpha v alpha. Momentum of the radium is mrvr. Okay. So since the momentum is conserved, the momentum gained by the alpha particle should be equal to the radium particle. Based on that, I can tell you m alpha v alpha or PR is equal to P alpha is equal to PR. Correct? And you remember this equation, E equals P square over 2M. Kinetic energy and momentum relationship is equal P square over 2M. Then, if I cross multiply, P square equals 2ME. Okay. So now, since both the particles have the same momentum, do you understand that to M alpha E alpha, should be equal to 2 MR ER. And P is the same for both. So P square is the same for both. So that means the 2ME product is the same for both. 2 M alpha E alpha should be equal to 2 MR ER. Correct? So I can cut the 2's. So basically M alpha E alpha equals MR ER. Okay?
So what happened to the square?
Darling, P square is equal to 2ME. So P is the same for both particles, means P square will be the same for both particles. P square of alpha particle is equal to the P square of the radius. Sorry, what is that particle? Nucleus? Radon or radium? Radium. P square of radium is equal to P square of the alpha particle. Okay, so which means the 2ME product of both will be the same. Now the alpha particle's mass is straightforward, which is 4.00260. 4.00260. U. Kinetic energy of the alpha particle is what I want. I will take it as E alpha. Okay. Mass of radium is 224.02021. And the ER is 5.5278. Minus E alpha. Do you understand that? From the total energy, which was released 5.5278, what we calculated in the previous part. From that, if you minus the kinetic energy of the alpha particle, you're going to get the ER. Okay. So now this is just one straightforward linear equation of E alpha. Solve this, you're going to get the answer. Okay. So on either side, the U's will cancel off. 4.00260 E alpha equals, take off the brackets, 224.02021 multiplied by 5.5278. That is 1238. Point 3389 minus 224.02021 E alpha. Bring the minus E alpha term to the left. So it will become 4.00260 plus 224.02021, which is 228.02281 E alpha is equal to 1238.3389. Finally, E alpha is equal to 5.43. Same answer. This is definitely an easier method for me. If you just understand that E is equal to P square over 2A. Okay. Right. That was what's next? $38, $37. Right, 37th one. Organism can be produced by firing calcium ions at a target of caliform atoms. Complete the equation for this reaction. Okay. So the neutron is 0, 1. 20 plus 98 is 180. You can see that is equal. Then 48 plus 249. 48 plus 249 should be 297. So we have here a mass number of 294. That means 3 is needed. It has to be 3 neutrons emitted. Okay. The calcium ions were accelerated to an energy of 245 mega electron volts. State how ions of this energy could be state how ions of this energy could be produced. 245 mega electron volts. Yes. Yeah, cyclotron, or maybe it's a one marker. They are asking. You can say cyclotron by accelerating it using a cyclotron or accelerating in a cyclotron. Right, guys. Part B: the calcium ions were accelerated. Done. Part 2: it is claimed that calcium ions with an energy 245 mega electron volts are traveling at relativistic speeds. Assess the validity of this claim. Mass of the calcium ion is 47.95 U. That's an easy one. Just calculate the speed of the particle and see whether it is close to the speed of light. So E, kinetic energy of the particle is half mv square. Kinetic energy is 245 mega electron volts. 245 into 10 to the power 6 electron volts into, to convert electron volts to joules, multiplied by 1.6 into 10 to the power minus 90. Half into mass of the particle is 47.95. (1.66) into 10 to the power minus 27 into V square. Okay, find the V from here. It's 3.138 into 10 to the power 7 meters per second. Okay, so claim is what? It is claimed that calcium ions with an energy 245 mega electron volts are traveling at a relativistic speed. Assess the validity of this claim. So we are getting the speed as 3.138 into 10 to the power 7 meters per second. The speed of light is 3 into 10 to the power 8 meters per second. So this is more than 10% of the speed of the sound. Sorry, speed of the light. So is it relativistic speed or not? I think yes. Yes, it's. What is the bound? Is there a boundary? 10% or 20% something. Yeah, but anyway, after you get this working, for the statement you will get a mark. You can mention it is more than 10% of the speed of light. It is more than 10% of the speed of light, or just more than 10% of the speed of light. So it is, huh? Just more than 10%, right? Hold on. Yeah. So 3 to 10 power 8 is speed of light. So 3 to 10 power 7 will be 10%. So this is just more than that. Yes, right? So you can write a statement, the speed is just more than 10% of the speed of light. So it is not moving at relativistic speed, or I can't remember exactly what it is, as 20% of something. I can't remember. So based on that, I mean, up to here you have done, no? So that part really doesn't matter whether it is relativistic or not. So no. So we can check and decide. So for now, I said not necessary. Fine. Part C.
So it is.
Yeah. Not relativistic speed, right? It's write that value for now. After later we will check what is the exact limit. Part C. The isotope of Og-94 is extremely unstable and decays by alpha decay. After 2.5 milliseconds, the sample contains 500 atoms of the sample. Calculate the original number of atoms in the sample. So we can use half-life is given. N equals N naught e to the power minus lambda t. So after a time of 2.5 milliseconds, the N remaining is 500 atoms. So 500 equals N naught into e to the power minus lambda is L into over T half. L into over the T half is 0.89 into T is 2.5 milliseconds. So e to the power minus L into over 0.89 into 2.5. 500 divided by that will be the answer, which is N naught equals. I'm getting 3,504 atoms. Are you getting that? Now what? Okay. Explain the precaution necessary when handling a sample of an alpha emitting isotope. Use your common sense and tell one. Reduce the exposure time. Oh, correct. And use long handles. Try to increase the distance between you and the source. Okay. No, you can't. They are not asking about storing. They are asking about handling. You can't store it inside a lid box and handle it. Okay, so you can say use long handles. That is also you can, yes. Right. Particularly for alpha particle, we can write use long handles and increase the distance between. Okay, guys, can you start with question number? There's one more. Yes, we'll do that. Can you start with question number 31? Question 31. 31, give a try. Thirty-one. Can't remember. Looks like yes. Yes. Right, okay, guys, 31st one. A student investigated the absorption of gamma radiation by iron. She placed a gamma source in a holder and set up a Geiger-Müller tube a short distance away. She placed thin sheets of iron between the GM tube and the source as shown. The student used 5 different thicknesses of iron and determined the count rate for each thickness. The count rate with no iron sheet in place is R0 after passing through an iron sheet. Of thickness x, the count rate R is given by the equation R equal to R0 e to the power minus mu x, an exponential decay equation, where mu is a constant. The student used her data to plot a graph. So LNR is in the y-axis, the thickness of the sheet is given, x in the x-axis. The student used the gradient of the graph to determine a value for mu and used this to estimate the half value thickness for the iron. What does this half value thickness means? It is the thickness of iron that would reduce the count rate to R0/2. The student uses a source that emitted gamma rays of energy 1.1 mega electron volts. Deduce whether the data the student obtained confirm this energy value. Half value thickness for 1.1 mega electron volt gamma rays in iron is 1.5 centimeters. It's a very simple question. Okay. So all you need to do is check the half thickness value. Okay. Half thickness value for this particular item, material, and see whether it is 1.5 centimeters. Your job is done. Okay. The student used a source that emitted gamma rays of energy 1.1 mega electron volts. Deduce whether the data student obtained confirms this energy value. Fine. So now, what is it? Ln initial R0 value is 6 point here. Initial R values, Ln value is 6 point. This is 6.678. This is 6.85. So I would take it as around 6.84 or 6.83. Am I right? That is the initial R0's value, Ln value. So if I take Ln R0, that is equal to 6.84. Let's say Ln R0 is 6.84, which is R0 equals e to the power 6.84. So the initial R, initial count rate, R is count rate, R0 is initial count rate. So e to the power 6.84. E to the power 6.84 is 934.489. This is the initial count rate. Okay. So now when the count rate becomes half, so what are they saying is the thickness, this is the thickness of iron that would reduce the count rate to R0/2. So half value thickness means the value of the thickness which will make the count rate to half of that initial value. So half R0 is going to be R0/2 is going to be that divided by 2, which is 467.245. This is the R0/2 value. So what is the Ln of that? Ln of R0/2 is going to be, Ln of that value is going to be 6.146. 85. So I can take it to 2 decimal places. 6.15. So now go back to the graph and check where is the LNR value is 6.15. 6.15 is 6.1 is here, 6.2 is here, 6.15 is here. So the thickness required is about 1.45 centimeters. Hence, thickness is 1.45 centimeters. Okay, these are thickness we are getting. So what are they saying? The half value thickness of 1.1 mega electron volt gamma rays is 1.5 centimeters. So what are we told to do? Deduce whether the data the student obtained confirms whether this is the energy. So after getting up to here, your job is done. From the 6 marks, you have got 5 marks. So the last statement, you can do it actually for this state either way. One can say yes, 1.45 centimeters is close to 1.5 centimeters. Yes, it is 1.1 mega electron volts. Another student can look it in a way, no, 1.45 is less than 1.5 centimeters and make the statement, no, it is not 1.1 mega electron volts. The thickness is less than that. Okay, understood. Both are fine. No, not really. You don't have any data about it. How? Any questions? Right, then how about guys, question 27. Page 40. Right. In France, scientists from many countries are working together to build the International Thermonuclear Experimental Reactor, ITER, in France. Okay. Do you know Sri Lanka is planning to put up a nuclear power plant? Yes. Is it nuclear fusion or fission? Fission. All the nuclear power plants are nuclear fission. There are no nuclear fusion power plants. So nuclear fusion reactions happens where? In the core of the star. So in astrophysics, we will learn about it in detail. So in the core of a star, nuclear fusion reactions happen. So artificially, it's very difficult to make a nuclear fusion reaction take place. For a nuclear fusion reaction to take place, You need really high temperature and pressure values. Okay.
So why don't
So-
they use that money to better the community?
Sorry.
Why don't they use that money for the Sri Lankan economy?
We will stick to physics. Okay. So, what were we discussing about? Yeah. So for nuclear fusion to happen, okay. Now, yeah, stars. So I have a very good answer if you all speak about Sri Lanka's electricity crisis. Okay, but I don't want to speak about it. I will take a lot of time unnecessary. Something. Okay. Do you know what is the Sri Lanka's peak demand of electricity? What is the demand? Huh? Fine. Then no point talking to you all about electricity. We'll stick to physics. Okay, listen. So if you, no. If in the future by any chance if you do an electrical engineering degree, you will know about it. Okay, listen. Anyway, for nuclear fusion to take place, you need very high temperature. And overall, guys, don't find faults in your country. Okay. Yeah, useless people. See the good and see what you can give it back to the country. Don't try to find faults. If you see any shortcomings, don't keep talking about it. Okay, see what you can do to fix it. As a citizen of the country, how you can contribute. It's like you're talking, okay, we have these problems in the country, as you're not part of it. Okay, we are all part of it. If your country is going through a bad season, you, your parents, your grandfathers, all are responsible. Okay. So just because everyone is talking against the government, you also don't be an idiot and do that. That's not the right thing to do. If the country is doing bad, we all have to take the responsibility of it. My parents, my grandfather, your grandfather, everyone is responsible. Okay. So don't just put the blame on someone. Okay. No, I'm saying, I mean, that is the South Asian mentality I have seen. You will not see this in a developed country. That is the reason they are developed and we are developing forever. Okay, there's no one to take the responsibility. What is a country? It is the people of the country, right? So we are all the country. Don't you understand that? There's no one who owns this country. The 23 million people, we are the country. So if the country is doing bad, we are doing bad. We are responsible for that. Do you understand that? The people of this country have been used to that method. Okay, blame someone. The politicians are responsible for that. That officer is responsible for that. That department is responsible for that. Who elected those politicians? Your parents, your grandparents, you. So you are responsible. So take the blame. Okay, see what you can do. What you can do to make it better, without just keeping on talking like these. The regular Sri Lankans don't be like that. Show your intellectual capacity being different from the others. Okay, don't do stupid things. Fine, don't these things. I will just keep talking. Okay, get back to work. No, that is not what I have to do. I have to understand what is my responsibility as a citizen. Do that. That's it. I don't have to be a politician to make Sri Lanka better. I will try. Always I have been doing wherever I am. I will try my best to make it better. You don't have to be a politician to do it. That is very stupid. Okay. So you do your individual responsibilities properly. That is more than enough. And stop complaining. Okay. Do your part. Get back to work. Question 27. Hereafter, don't talk to me about these things. Okay. In France, Let them do whatever they want. Okay. On the ITER website, it says fusion is the energy source of the sun and stars. In the core of these stellar bodies, hydrogen nuclei fuse into helium nuclei and release tremendous amount of energy. Explain why energy is released when hydrogen nuclei fuse to form helium nuclei. So there's energy is released because there is a mass deficit. Okay, so hydrogen nuclei fuse to form helium, no? So when hydrogen fuse, there is a mass deficit, mass reduces. So equivalent amount of energy is produced according to the equation E equals mc square, right? There is a mass deficit or mass reduces. There is a mass deficit. So an equivalent amount of energy is produced.
So can you
Okay.
tell the answer?
There is a mass deficit. So an equivalent amount of energy released. Right, part B. It is hoped that the ITER will be the first fusion device on Earth to maintain nuclear fusion for long periods of time. Long periods of time. To achieve fusion in ITER, a hot plasma is used. The plasma must be at extremely high temperature, have sufficient density for fusion. Explain why each of these two conditions must be met. The 4 mark. Guys, now listen. Extremely high temperature is required why for nuclear fusion to happen. If you take two nuclei, both are positively charged. So they naturally have an electrostatically repulsive force. Listen. They have an electrostatic repulsive force. So they try to move away from each other. They will not want to come and fuse together naturally. Okay. So if you want to make them fuse together, you have to force them to come together. Correct? So to force them to come together, you have to supply a high kinetic energy and make them move together. To provide that high kinetic energy, what do you need? High temperature. Okay, that is one thing. So it has to be at very high temperature, that's fine. Have sufficient density for fusion. So what is that sufficient density for fusion? That means now this fusion should happen at a good rate. There should be a good amount of fusion reactions happening per second so that that fusion will sustain. Okay, because when this fusion happens, it will create energy. It will create energy, and that energy is used to fuse further. So if you want to sustain the fusion happening, the density, that means the amount of fusion happening for a second, the rate of fusion happening has to be high. For the rate of fusion happening to high, the density has to be high. Right under that. In a small space, more number of nuclei. Okay. Right. Nuclei should have high kinetic energy. To overcome repulsive forces and fuse together. Full stop. So the temperature has to be extremely high. Full stop. For the fusion to sustain, for the nuclear fusion to sustain, the reaction should happen at a higher rate. For the fusion to sustain, reaction should happen at a higher rate. So the density of the nuclei should be high. Right. Part C. The graph shows the variation of binding energy per nucleon with proton number Z. Binding energy per nucleon is given in the y-axis. Z, the nucleon number, is given in the x-axis. In one possible fusion reaction, the nucleus of hydrogen 2 fuses with a nucleus of hydrogen 3. A nucleus of helium 4 and a free neutron are produced as shown in the following nuclear equation. Determine the energy in megaelectron volts released when a nucleus of hydrogen 2 fuses with a nucleus of hydrogen 3. Guys, now stop and look at the screen. Let me do it. Now what we have is binding energy per nucleon values. Okay. So if you take the hydrogen 2, it has a binding energy per nucleon of 1.1 mega electron volts. And hydrogen 3 has a binding energy per nucleon value of 2.8 mega electron volts. And the helium 4 has a value of 7. These are the values of binding energy per nucleon. Okay. So now what happens is, when it is fusing, give me 30 seconds, please. Okay, listen. Guys, now in this nuclear fusion reaction, what happens is, if you take the hydrogen 2, and hydrogen 2 has 2 nucleons, listen to me carefully. Hydrogen 2 has 2 nucleons. Okay. Hydrogen 3 has 3 nucleons. Helium 4 has 4 nucleons. So here what happens is, the hydrogen 2 that disintegrates. The 2 nucleons get separated. And then same with hydrogen 3, it disintegrates. The 3 nucleons get separated. Okay. Now how many nucleons you have? 5 nucleons. From that 5 nucleons, 4 nucleons combine together to form helium nucleus. Okay. Now listen carefully. So to disintegrate the hydrogen 2 and hydrogen 3, you need to supply energy. Am I right? So when helium 4 is formed, it releases energy. Am I right? When the helium 4 is formed, the energy released is more than the energy that you have to supply to disintegrate hydrogen 2 and hydrogen 3. Okay. So that means overall there is an energy release. Do you understand what I'm saying? Fine. Now, the energy that you have
Yeah, I
to
understand,
supply
sir, but then like where does the excess energy that's released after the fusion comes from?
from the mass deficit.
Okay.
Okay. Right. Now, E1 is the energy that you have to supply to disintegrate the hydrogen 2 and hydrogen 3. So, hydrogen 2 has a near binding energy per nucleon of 1.1, and there are 2 nucleons, so 1.1 into 2. Plus, hydrogen 3 has a binding energy per nucleon of 2.8, and there are 3 nucleons, 2.8 into 3. So, the energy that you need to supply is 10.6 mega electron volts. Okay. This is the energy that you need to supply to disintegrate them. So the energy released while the formation of the helium 4 is 4 into 7, which is 28 mega electron volts. Because the helium has 4 nucleons and its binding energy per nucleon is 7. So the energy released is 4 into 7, 28 mega electron volts. So what is the energy released in this reaction? It's going to be 28 minus 10.6, 17.4 mega electron volts. No, it doesn't have an energy. Because it doesn't have what is binding energy when you what is binding energy? Then by definition. For all the nucleons to be separated to infinity, the amount of energy need to be supplied. That is binding energy by definition. So if a neutron is single, if it is not, it doesn't have a binding energy, right? Yeah, that kinetic energy that we don't take into account, maybe a small kinetic energy it can have, that is not taken into account. Okay. Mm-hmm. Yeah, you can do it. Okay, done. Right. Guys, you can take a small break. Now it's 9:32. See you at 9:40, 7-8 minutes break. 9:40 sharp. So, yeah, on time. Right, guys. There are a few more questions remaining from this tube. I guess it's less around maybe another 3-4 questions. So please complete it yourself. And if there's anything, bring it on the next day. Okay. Increase the temperature. As a physics student, don't tell reduce the AC. Reduce the AC meaning what it means is we have to reduce the number of AC units in this classroom. So that means I have to remove one AC from this class. There's nothing. Reduce the temperature or increase the temperature. If you want to make it hotter, increase the temperature. Okay. Huh? I have increased that. Guys, okay, let's start with the next topic. So under Unit 5, we have done 2 topics, 2 more to go. You have got the tube for those 2. So let's just get it started. Right on the topic. Oscillations. Oscillation. Right. So guys, now when you take an object which is attached to a spring, and when you pull it down a bit and release it, it will move up and down. Okay, it is an oscillation. Okay, or if you take a simple pendulum which is hanging vertically, if you move it a bit to one side and release it, it will keep on moving forward and backward about a fixed point. That is an oscillation. Draw this diagram. And right under that, when a force is applied, on a spring as shown in the above diagram, and when the force is released, when a force is applied on a spring, as shown in the above diagram, and when the force is released, the object will move up and down about a fixed point. Move up and down about a fixed point. Full stop. This repetitive motion, about a fixed point, is known as an oscillation. Okay. This is repetitive motion about a fixed point is known as an oscillation. Full stop. And right below that. Another example for oscillation will be a simple pendulum. Another example of oscillation will be a simple pendulum. So just draw a diagram to show a simple pendulum. Guys, the tute, we will not be using it today, but don't forget to bring it next class. They have your names written inside. Okay. Right on the next subtopic. Now guys, this oscillation becomes a simple harmonic motion when a couple of conditions are satisfied. Okay. An oscillation becomes a simple harmonic motion. There is a definition of simple harmonic motion where there are two key points to consider. If those two key points are satisfied, an oscillation becomes a simple harmonic motion. Okay. Subtopic, simple harmonic motion. Right under that. An oscillation becomes a simple harmonic motion an oscillation becomes a simple harmonic motion. When the following two conditions are satisfied. When the following two conditions are satisfied. Number one, acceleration of the object is directly proportional to the displacement. Acceleration of the object is directly proportional to the displacement. So write it, A is directly proportional to X. Number 2, acceleration and displacement are always in opposite directions. Acceleration and displacement are always in opposite directions. Okay. So an equation, a characteristic equation of an object which is in simple harmonic motion is this: A equals minus omega square x. Take it down. A is the acceleration, x is the displacement, omega is the angular frequency. Okay. Omega is angular frequency. As I'll explain you with this example, let's say now you have this spring. There's an object attached to a spring. This is the position of the spring. Then you pull it down and you release it, and then it starts oscillating. So how does it move? Let's say the object is here. It keeps moving up and down. Keeps vibrating. Is oscillation. Okay. So now let's say during the oscillation, now this is the equilibrium level. Now let's say the object is at a position somewhere here. It has got extended during its oscillation at a particular instant. So the displacement is this way, right? Acceleration will be this way. Okay. Acceleration is against the displacement. Now let's say in another instance, this is equilibrium level. Let's say the spring is here. The object is here. The displacement is this way. The acceleration will be in the opposite direction, this way. Understood? In a simple harmonic motion, the acceleration will be always in the opposite direction to the displacement. In other words, acceleration will be always directed towards that equilibrium point, equilibrium level. Understood? When the displacement is down, the acceleration is up. When the displacement is up, the acceleration is down. Always it will be directed towards this equilibrium level. Is that okay? So that is what the minus sign here says. The A is equal to minus omega square x. The minus sign signifies that A and the x are always in opposite direction. Okay.
So what's
With it.
W, sir? What's W? W.
Omega. This is omega. That is the angular frequency. Right? So, and also,
Yeah.
A is directly proportional to x. When the displacement is increasing, the acceleration will also increase. So that you know by practice, if you take a spring, the longer you extend and release, higher it will have the acceleration. Isn't it? If you pull it a bit and leave it, it will have a small acceleration. If you pull it down a lot and release it, it will have a high acceleration. And that acceleration will reduce as the displacement is reduced. Or the acceleration will increase as the displacement is increased. So these are the two characters. One is acceleration is directly proportional to the displacement. The other one is the acceleration and displacement are in opposite direction all the time, which is given by the equation A equals minus omega square x. So right under that, the minus sign in the above equation signifies that A and X are in opposite directions. Okay, so guys, omega equals 2 pi over t, where t is the time period of the oscillation. Capital T is the time taken for one complete oscillation. Okay, right. That's enough for today. We'll continue from this point on the next day. So that is going to be in 2024, right? So guys, you can make it a point. Listen. Right? You have 5 more months. We are done with unit 4. If you, that is about minimum 20 weeks. You do at least on average 1.5 papers a week, which is 3 papers in 2 weeks. I'm talking about. Okay, on average, if you do 1.5 papers a week for 20 weeks, you can do 30 papers. Okay, doing 2 papers in 14 days, if you can't do as an advanced level student, you don't deserve a good grade for A levels. Okay, so be organized. I'm telling you, just keep doing the unit 4 papers again and again and again and again. Definitely, you will get the best possible grade that you can get with your capacity. Okay, the only way that you want to improve is keep on doing papers. Do a paper. If there's any area that you can't remember, immediately after doing the paper, go and check the theory. Don't keep on reading textbooks. Don't keep on reading theory. You're not going to get anything. Do a paper, then and there. Once you're done it, mark it. If you think, okay, there are certain areas you can remember, immediately after the paper, allocate another half an hour to 1 hour. Go back to the theory and check it, get it done, fix it. The next day, do another paper. Do the same thing. Okay? Trust me, that is the best way of learning physics, getting better at physics. Same thing I would say, even if you're doing maths, do the same thing. Keep doing papers. There's no theory. The theory is very little. It's how you apply the theory. So how you will improve it? Only by doing papers and questions. There's no other way. Okay? So this holiday is for me, not for you. Okay? You can have holidays once you are done with your studies, and once you're done with your A levels and your higher studies, after maybe another 4 or 5 years, you can have very relaxful, nice holidays. Okay, when I was a student, I had a much harder time than you all. Okay, so you don't have to compare yourself with what I'm doing now. So you play the role of a student. Your primary, secondary, and every objective has to be to do your exams with. Nothing else. So do the right thing at the right time. So don't enjoy these holidays. I'm clearly telling you, this is not for you to enjoy, for me to enjoy. Okay, you can do that later. So focus on your studies and happy holidays with your studies. Bye, people. See you. Take care.
Thank you, sir. Bye. Thank you, sir.
Bye. Take care. Thanks for